Tonight, we're going to talk about one of the strangest discoveries in modern astronomy. A telescope that has only been fully operational for a few years has found objects that no one expected. Tiny, compact, intensely red points of light scattered across the deepest images of the early universe. They sit in a period of cosmic history where, according to every model we have built over the past 50 years, they simply should not exist in the form we observe them. They are, by every rule we know, impossible. And by the end of tonight, you are going to understand what these objects are, why they sent shockwaves through the field of astrophysics, and why the most compelling answer turned out to be a theoretical prediction that had been sitting mostly unread in a published paper for 16 years, waiting for a telescope powerful enough to prove it right. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The James Webb Space Telescope launched on the 25th of December, 2021. It had been in development for more than 2 decades, a project that began in the late 1990s as the planned successor to the Hubble Space Telescope, was originally expected to cost around $500 million and ended up costing nearly $10 billion. The delays and cost overruns were not the result of mismanagement alone. They were the result of genuine engineering difficulty. Webb is the most complex space observatory ever built by human hands. Its primary mirror, made up of 18 hexagonal gold-coated beryllium segments, stretches 6.5 meters across. That mirror could not be launched as a single rigid structure. It was too large for any existing rocket fairing. It had to fold up, origami style, fit inside the rocket, and then unfold in deep space, one segment at a time, over the weeks following launch. The same was true of the sunshield, a 5-layer, tennis court-sized membrane designed to block the heat and light of the sun so that the telescope's instruments could be kept cold enough to detect faint infrared signals. Each layer of the sunshield had to fold up for launch and then deploy in sequence once the telescope was in space. Hundreds of mechanical release points, each of which had to work flawlessly in the vacuum of deep space, where no repair mission was possible. The margin for error was essentially zero. The launch finally came, and it was flawless. The deployment that followed was tense engineers and scientists watching each step, aware that a single failure in any of hundreds of systems would end the mission. But it worked. By July of 2022, the telescope was fully commissioned and returning scientific images. Images that immediately surpassed everything that had come before them. The reason Webb could do this, the reason it can peer deeper into the universe and further back into cosmic time than any previous instrument, comes down to one fundamental physical fact. It was built to see the universe in infrared light. The universe is expanding. It has been expanding since the Big Bang, and that expansion carries a consequence for every photon traveling through it. As light travels through expanding space, the space itself stretches. The wavelength of the light stretches along with it. Radiation that began its journey at ultraviolet wavelengths, emitted by a hot young star in the early universe, has its wavelength elongated as it crosses the billions of light-years of expanding space between its source and us. By the time that light arrives at our detectors, it may have shifted from ultraviolet into the visible range, or from visible into the near-infrared. Light from the most distant objects, the objects at the highest redshifts, emitting radiation when the universe was only a few 100 million years old, has been stretched so far that it arrives in the mid-infrared range. Hubble was designed primarily for optical and ultraviolet observation, with some near-infrared capability added in later years through instrument upgrades. It was not built for the wavelengths where the earliest universe glows. Webb was. Its detectors, its instruments, and its entire thermal design were oriented toward the infrared. The sunshield that keeps the telescope cold is not a luxury. It is a necessity. An infrared telescope operates by detecting tiny amounts of heat radiating from extremely distant objects. If the telescope itself were warm, its own thermal emission would overwhelm the faint signals from the early cosmos. Webb operates at a temperature of around -233 degrees Celsius, specifically to keep its own thermal noise low enough that the instruments can detect the signals they are built to find. That design paid off immediately in the first deep field images. Scattered across those images were small, intensely red, compact points of light. They were not subtle once you knew what to look for. They stood out against the background of other galaxies and stars. Because of their distinctive color and their compactness, dots of deep red in images where most objects were blue, white, or multicolored diffuse structures. They appeared in every deep field image, Webb returned. Not occasionally. Every time. In some of the deepest fields, they were present in numbers that surprised everyone who reviewed the data. They were extremely compact, unresolved, even at Webb's angular resolution, meaning the telescope could not distinguish their spatial extent on the sky. They appeared as points, like stars, rather than the extended, diffuse structures you would expect from a galaxy at any stage of its development. They were red in a way that placed their peak emission in the near-infrared, consistent with objects at high redshift whose light had been stretched during its long journey across expanding space. And they were concentrated at redshifts, corresponding to the era roughly 500 million to 1 billion years after the Big Bang, the period when the universe was completing its transition from the Dark Ages into the age of galaxies and stars. These objects had no established category. They did not fit the morphological description of any known type of galaxy. They were too compact and too bright at those distances to be individual stars. They showed features in their spectra that were inconsistent with standard active galactic nuclei as they had been understood for decades. They were something new, something outside the established inventory of cosmic structures. That is genuinely rare in modern astronomy. The sky has been surveyed so extensively over the past century that finding a fundamentally new category of object requires either a telescope with capabilities that previous instruments lacked, or access to a regime of the universe that had simply been invisible before. Webb provided both. In early 2024, an astronomer named Geordie Matthey and his colleagues published a formal catalogue of the objects in the Astrophysical Journal. The paper documented their properties, measured their redshifts, analyzed their spectra, and gave them a name: little red dots. The name was deliberately informal. In the technical literature, they also appeared under the more descriptive label of broadline H-alpha emitters, referring to a specific spectroscopic feature they shared. But the informal name stuck because it was short, it was memorable, and it was accurate. They were small. They were red. No one knew what they were. By the time the catalogue was published, more than 1,000 had been identified in Webb's data. That number has continued to grow with each new survey. In some of the deepest fields, approximately 1 in every 100 objects at the relevant redshifts turns out to be a little red dot. That is not an anomaly or an oddity. That is a population. A substantial, consistent population of objects that the entire field of astronomy had never seen before. sitting in a part of the universe and a period of cosmic time that had been, until Webb, essentially invisible. To understand why the little red dots are such a profound problem, you need to understand what the early universe is supposed to look like. Cosmology, the science of the origin, structure, and evolution of the universe as a whole, is built on a framework developed over roughly a century of observation and theoretical work. It is called the Standard Cosmological Model, sometimes abbreviated as lambda CDM, a reference to the two main ingredients beyond ordinary matter and radiation that the model requires. The lambda refers to the cosmological constant, Einstein's term, for the energy of empty space that is now thought to drive the accelerating expansion of the universe. The CDM refers to cold, dark matter, the mysterious form of matter that does not emit or absorb light, but that nevertheless gravitates, and that appears to make up the majority of the universe's matter content. Together with ordinary baryonic matter and radiation, these ingredients produce a framework that has been tested against observations at every scale and every cosmic epoch accessible to our instruments, and that has consistently held up. At the foundation of this framework is a detailed picture of how the cosmos evolved from a hot, dense initial state to the structured universe we observe today. In the very first fractions of a second after the Big Bang, the universe was unimaginably hot and dense. In the first few minutes, temperatures fell to the point where protons and neutrons could combine into the first atomic nuclei, mostly hydrogen and helium, with trace amounts of deuterium, helium-3, and a small fraction of lithium. This process, Big Bang nucleosynthesis, produced the raw material from which all subsequent structure in the universe would eventually be assembled. For the next 380,000 years, the universe remained too hot for electrons to bind to atomic nuclei. It was a plasma, a hot, opaque sea of charged particles. Photons scattered constantly off free electrons and could not travel any meaningful distance without being absorbed and re-emitted. The universe was opaque to its own radiation. Then, as it continued to cool, electrons and protons combined to form neutral hydrogen atoms for the first time. The plasma cleared. Photons could suddenly travel freely through space, unimpeded, in all directions. The radiation released at that moment has been traveling ever since, cooling as the universe has expanded around it. We observe it today as the cosmic microwave background, a faint, nearly uniform glow of microwave radiation coming from every direction in the sky. It is the oldest light in the universe, a snapshot of the cosmos at an age of roughly 380,000 years. It has been mapped in extraordinary detail by space observatories, including COBE, WMAP, and the Planck satellite. The tiny temperature fluctuations, imprinted on the cosmic microwave background variations of roughly 1 part in 100,000 from place to place, reflect the density fluctuations in the early plasma. Those fluctuations were the seeds of all the structure that would later form. After recombination, the universe entered what astronomers call the cosmic dark ages. There were no stars. There were no galaxies. There were no sources of light of any kind other than the fading remnant of the Big Bang itself. The universe was filled with cold, neutral hydrogen gas and dark matter, both slowly being pulled together by gravity into the first dense concentrations of matter. Those tiny density fluctuations from the early universe grew over time under the influence of gravity. Slightly denser regions pulled in surrounding material, growing denser still. Less dense regions lost mass to their surroundings and emptied out. Over hundreds of millions of years, this process transformed the near-uniform early universe into an increasingly structured cosmos, with filaments and nodes of matter forming a cosmic web, and the spaces between them becoming the vast voids that make up most of the observable universe's volume. Then, around 200 million years after the Big Bang, the precise timing is still being refined. The first stars ignited. Gas in the densest regions had collapsed far enough that temperatures and pressures in the cores were sufficient for nuclear fusion to begin. The cosmic dark ages ended. For the first time since the Big Bang, the universe had internal light sources. These first stars, population, 3 stars, were fundamentally different from the stars we observe around us today. They formed from gas that contained only hydrogen, helium, and a trace of lithium. No carbon, no oxygen, no iron, no silicon. Without heavy elements, the gas could not cool as efficiently as modern interstellar gas does. And the stars that formed from it were likely enormous, possibly hundreds of times the mass of our Sun. They burned with extraordinary brightness and were short-lived. Within a few million years, they exhausted their fuel and ended their lives in violent explosions, seeding the surrounding gas with the heavy elements forged in their cores. Each successive generation of stars was born from gas enriched by the generations before. The universe's chemistry grew progressively richer. From those first stars, the cosmos began building up the elements that would make rocky planets, oceans, and eventually living things possible. From that point forward, the universe assembled structure, first individual stars, then small proto-galaxies gathering around dense concentrations of dark matter, then larger structures growing through mergers and the accretion of surrounding gas. The process is hierarchical. Small things form first. Larger structures grow from the accumulation of smaller ones over cosmic time. This picture is not merely theoretical. It is backed by decades of observations, computer simulations, measurements of the large-scale distribution of galaxies, and the detailed pattern of fluctuations on the cosmic microwave background. It is one of the most thoroughly tested frameworks in all of science. The era where the little red dots live 500 million to 1 billion years after the Big Bang falls squarely in the early stages of that hierarchical assembly process. Galaxies, at that age, should be young. They should be relatively small. They should be assembling their stellar mass gradually through a combination of internal star formation and mergers with other small structures. The universe has simply not had enough time to build anything much more massive than a few percent of the Milky Way's stellar mass. The models that predict this are not vague. Galaxy formation simulations, some of the most computationally intensive projects in all of astrophysics, running on the world's most powerful supercomputers, are quite specific about what the galaxy population should look like at those redshifts. Faint and irregular. Blue, indicating ongoing but modest star formation. Relatively extended in their structure, and not yet very massive. What the little red dots appear to be is the opposite of every one of those predictions. The first quantitative measurements came with an immediate sense that something was fundamentally wrong. When astronomers tried to estimate the stellar masses of the little red dots using their observed brightness, they returned numbers that broke every formation model built over the previous half-century. A galaxy's brightness is proportional to the number of stars it contains, and from the brightness, you can infer the stellar mass if you make reasonable assumptions about the types of stars present. The masses came back far too high. Some of the little red dots appeared to contain stellar masses comparable to the Milky Way, a galaxy that has been accumulating mass for roughly 13 billion years. Finding anything comparable in objects only 500 million years old was not a minor deviation from the models. It was a factor of 10 or more beyond what the standard framework permitted. A team at Penn State gave the objects an unofficial name: universe breakers. The name was not hyperbole. It reflected a genuine assessment of what the data appeared to show. If these objects genuinely contained the masses their brightness implied, the cosmological models that had been built, tested, and refined over 5 decades of observational astronomy were in serious trouble. But the mass problem was only the beginning. The spectra of the little red dots, the detailed breakdown of their light by wavelength, were equally unsettling, and in a more complex way. To appreciate why, it helps to understand what a spectrum actually tells you, and why astronomers treat spectroscopy as one of the most powerful tools they have. Every element in the universe interacts with light in a specific and characteristic way. The electrons bound to an atom can only exist in certain discrete energy states defined by the laws of quantum mechanics. When an electron jumps from a higher energy state to a lower one, it emits a photon with a specific energy and therefore a specific wavelength. When an atom absorbs a photon, it must be a photon with exactly the right energy to cause a transition between allowed states. These transitions are fixed by physics and do not vary. Hydrogen always absorbs and emits at the same set of wavelengths, whether the hydrogen is in our Sun, in a galaxy 10 billion light-years away, or in a laboratory on Earth. Helium has a different set. Oxygen, carbon, calcium, iron. Each element has its own unique spectral fingerprint. A spectrum is therefore an extraordinarily information-rich measurement. From the spectrum of a distant object, you can determine its composition, its temperature, the density of its gas, the velocity of that gas relative to Earth, and, through the systematic redshift of all the spectral lines together, how far away the object is and how long ago the light was emitted. The spectra of the little red dots showed a distinctive and troubling shape that astronomers had rarely seen anywhere. In the ultraviolet part of the spectrum, the light was relatively bright. Then it dropped sharply over a very narrow wavelength range. Then it rose again in the red and optical. The overall shape was like a pronounced V, a steep cliff on the ultraviolet side and a rising slope on the red side. The edge of that cliff occurred at a specific wavelength, 364.6 nanometers in the rest frame of the object. This is the wavelength of the Balmer break. The Balmer break is produced by hydrogen, specifically by hydrogen atoms in their lowest energy state, absorbing photons that are energetic enough to ionize them to knock their electrons completely free. Photons with wavelengths shorter than 364.6 nanometers have enough energy to do this. Photons with longer wavelengths do not. The result is that a cloud of neutral hydrogen gas is essentially opaque to light below that wavelength and relatively transparent above it. An object surrounded by or embedded in a substantial amount of neutral hydrogen therefore shows a sharp drop in its spectrum right at that wavelength, a clear edge. The presence of a strong Balmer break carries a secondary meaning in galaxy science. In a galaxy with a population of old, evolved stars, stars that are billions of years old and have long since left the hot, blue main sequence, the light output is dominated by cooler, redder stars that are in advanced stages of their stellar lives. These older stellar populations naturally produce spectra with strong Balmer breaks because the light from the hot cores of the galaxy has been largely absorbed before it can escape. So, a strong Balmer break typically signals an evolved, mature stellar population, the kind you find in old, well-established galaxies that have been forming stars for billions of years. The little red dots had Balmer breaks among the strongest and sharpest ever measured at those redshifts, much sharper than theorists expected to find in objects from that era of cosmic history. And that created a direct and inescapable contradiction. A very strong Balmer break implies a galaxy old enough to have developed an evolved stellar population. But the universe at the redshifts where these objects live was not old enough to have produced such populations. The universe itself was less than 1 billion years old when this light was emitted. There was not enough time for galaxies to have accumulated the kind of evolved stellar populations that produce breaks that sharp. The spectrum was saying two things simultaneously, and those two things were physically incompatible. The first hypothesis offered to resolve the contradiction was the starburst galaxy model. A starburst galaxy is a galaxy undergoing an extreme and temporary episode of elevated star formation, usually triggered by an interaction or merger with another galaxy. Starbursts are well observed and well understood. When two galaxies come close to each other, or collide, the gravitational interaction can funnel large quantities of cold gas into the central regions of one or both galaxies. Gas that was previously spread across a diffuse disk gets compressed into a relatively small volume. When the compression is sufficient, gravity overwhelms the internal pressure of the gas clouds and they collapse into new stars. The result is a star formation rate that can exceed normal rates by factors of 100, 1,000, or even more in extreme cases. The Milky Way forms roughly 1 to 3 new stars per year in its current quiet state. An extreme starburst can form thousands of solar masses of new stars every year. Starburst galaxies have been studied extensively at lower redshifts and are recognized by a set of distinctive observational signatures. They are compact in their star-forming regions. They are bright because the many young massive stars produce enormous luminosity. They are surrounded by dust, produced by the deaths of the first generation of massive stars, and that dust reddens the emerging light by preferentially absorbing and scattering shorter blue wavelengths. A starburst region embedded in its own dust looks red. It looks compact, and it produces a Balmer break from the hydrogen gas being consumed and disrupted in the star formation process. When astronomers first encountered the little red dots, the starburst hypothesis appeared to check nearly every box. Compactness, consistent with a concentrated starburst region. Redness, consistent with dust absorption, preferentially removing blue light. Brightness, consistent with an elevated rate of star formation. Strong Balmer break consistent with the hydrogen gas associated with the starburst activity. For a considerable stretch through 2023 and into early 2024, the starburst interpretation was the leading model. Papers were written within this framework. Progress seemed to be happening. Then, a specific quantitative test broke the hypothesis, and it was not a subtle test. In late 2024, a research team at the University of Texas at Austin, led by the astrophysicist Caitlin Casey, published a careful analysis that exposed the starburst model's fatal weakness. The logic was as follows. In any starburst galaxy, the amount of dust present is tightly linked to the number of stars that have formed. Massive stars produce dust when they reach the end of their lives in supernova explosions, scattering heavy elements and solid grains into the surrounding medium. The more stellar mass a system has accumulated, the more supernovae have occurred, and the more dust has been produced. This relationship between dust mass and stellar mass has been measured empirically in hundreds of galaxies across a wide range of masses and star formation rates. It holds with a relatively small scatter. You cannot have a galaxy with a large stellar mass and essentially no dust. The physics does not permit it. Dust that has been warmed by surrounding stellar radiation radiates in the far infrared at wavelengths corresponding to its temperature. Webb's mid-infrared instrument, combined with ground-based far-infrared observatories, should have been sensitive enough to detect the thermal emission from the dust mass implied by the stellar mass estimates. When Casey's team looked for that emission, it was absent, not marginally below the predicted level, almost entirely absent. The dust they could detect from the little red dots amounted to less than 1% of what the starburst hypothesis required. 2 orders of magnitude short. No calibration, uncertainty, and no modeling assumption can bridge a gap of that size. If the dust was not there, the starburst interpretation was not the answer. A second, independent problem reinforced the conclusion. To explain the observed brightness of the little red dots using stars alone without any additional energy source, the stellar density within the objects would need to be extraordinary. Not just high, but physically unstable. Stars packed at those densities would undergo frequent gravitational interactions. Close encounters would perturb stellar orbits, exchange energy, and gradually disperse the structure. Actual stellar collisions would occur at rates that would dramatically alter the system over timescales shorter than the age of the universe at that point in cosmic history. A stable, long-lasting, bright stellar system was not possible at those densities. The starburst model was over. The second candidate was already in hand. If the light of the little red dots was not coming from stars, there is exactly one known mechanism in astrophysics capable of producing this much energy from a compact central point. A supermassive black hole, actively accreting surrounding gas. When a black hole at the center of a galaxy is pulling in large quantities of gas, that gas cannot fall straight inward. Conservation of angular momentum forces it to spiral inward through a flattened, rotating structure called an accretion disk. As the gas spirals inward through the disk, friction between adjacent layers heats it to extreme temperatures. The innermost regions of an accretion disk around a supermassive black hole can reach tens of millions of degrees. At those temperatures, the gas radiates copiously across an enormous range of wavelengths, from radio waves through infrared, optical, ultraviolet, X-rays, and into the gamma-ray range. An actively accreting supermassive black hole can outshine the combined light of all the hundreds of billions of stars in the surrounding galaxy. The light comes from a region no larger than our solar system, yet it exceeds the output of an entire galaxy of stars. That concentration of power arises purely from the release of gravitational potential energy by infalling gas. These objects, called active galactic nuclei in general, and quasars in their most luminous form, are extremely well studied. Thousands have been catalogued at many different redshifts. Their spectral properties are understood in detail. And when astronomers took careful spectra of the little red dots, they found a feature that appeared to confirm the active nucleus picture. The hydrogen emission lines in the spectra were broad, not narrow, sharp lines like those from gas at low velocities. Wide, smeared-out features spanning a range of wavelengths. In active galactic nuclei, broad emission lines have a specific and well-understood meaning. They are produced by gas orbiting very close to the central black hole at extremely high velocities in a region called the broadline region. The gas moves so fast that different parts of it are moving toward or away from us at very different speeds. Some gas is approaching us as it orbits, shifting its emission lines to shorter wavelengths. Some is receding, shifting them longer. The net effect, integrated across the entire broadline region, is to smear the emission line across a wide range of wavelengths. The width of a broad emission line is therefore a direct measure of the velocity of the gas in the broadline region. And the velocity of that gas reflects the gravitational field of whatever sits at the center. The broader the line, the faster the gas, and the more massive the central object. In the little red dots, the hydrogen emission lines were broad enough to imply gas moving at velocities of more than 2 million miles per hour. Nothing in the universe, other than a supermassive black hole, can accelerate gas to those velocities within such a compact region. The active galactic nucleus hypothesis had real quantitative spectroscopic evidence behind it. Two problems, however, would bring it down, each one a fundamental contradiction with the expected behavior of standard active galactic nuclei. The first was X-ray emission. Active black holes do not limit their radiation to optical and infrared light. The innermost regions of an accretion disk, compressed and heated to the highest temperatures, radiate copiously in the X-ray band. This is a fundamental and unavoidable feature of active accretion onto a compact object. X-ray emission from active galactic nuclei was detected in the 1960s and has been studied intensively ever since. The Chandra X-ray Observatory, in orbit since 1999, has catalogued tens of thousands of X-ray sources, many of them active galactic nuclei. The correlation between optical luminosity and X-ray luminosity in active galactic nuclei is thoroughly established. If you see a bright, active galactic nucleus in the optical, you expect a corresponding bright source in the X-rays. When Chandra and the European Space Agency's XMM Newton Observatory were pointed at the positions of the little red dots, the expected X-ray emission was not there. The objects were either entirely invisible in the X-ray band or far below the detection limit that active black holes at their optical luminosity should easily exceed. This was not a small discrepancy. Active black holes produce X-rays. That is among the most observationally well-established facts in all of astrophysics. The little red dots did not conform to this, and no straightforward modification of the standard active galactic nucleus picture could explain the absence. The second problem was the relationship between black hole mass and host galaxy mass. In the local universe, there is a tight and reproducible relationship called the Megorian relation between the mass of a galaxy's central black hole and the total stellar mass of the surrounding galaxy. Roughly, a galaxy's central black hole contains about 0.1% of the galaxy's total stellar mass. Small galaxies have small central black holes. Large galaxies have large central black holes. The two grow together, co-evolving through feedback processes that are not fully understood in detail, but that consistently maintain this ratio across a wide range of galaxy types and environments. The Megorian relation holds for the Milky Way. It holds for nearby elliptical and spiral galaxies. It holds for galaxies measured at moderate redshifts. It is one of the most robust empirical relationships in all of galaxy science. When researchers applied the standard spectroscopic technique using the width of the broad emission lines to infer black hole mass to the little red dots, the implied masses violated the Magorian relation by spectacular factors. The black holes were not 1/10 of 1% of their host galaxies. They were 10%. In some cases, they appeared to be as massive as the entire surrounding stellar system. They were 100 to 1,000 times larger than the relationship allows. The astrophysicist Fabio Pacucci at the Harvard and Smithsonian Center for Astrophysics summarized the situation in terms that circulated widely. If the little red dots contain black holes, those black holes are far too large for the size of the surrounding systems. If they contain only stars, the stellar density is physically impossible to sustain. Both standard categories had failed, not in ways that could be fixed with minor adjustments, in fundamental ways that required abandoning the established frameworks entirely. By the end of 2024, a substantial part of the field had arrived at a deeply uncomfortable conclusion. The existing frameworks were inadequate. Not wrong in every detail, but missing something important, something that, when properly understood, would require a conceptual revision in how we think about the earliest phases of black hole growth in the universe. The situation called for a new approach. At the Max Planck Institute for Astronomy in Heidelberg, Anna de Graaf had been planning a systematic observational campaign specifically designed to study the little red dot population in depth. She called the survey Ruby's Red Unknowns, Bright Infrared Extragalactic Survey. The acronym was accurate. These were red objects, bright in the infrared, located beyond the Milky Way, and thoroughly unknown. Between January and December of 2024, de Graaf and her team used nearly 60 hours of Webb observing time to collect spectra of 4,500 distant galaxies. 60 hours on the most powerful space telescope ever built, dedicated almost entirely to understanding a population of objects that had been discovered only 2 years earlier. Within that sample, they identified 35 objects fitting the little red dot profile. Most were already known from public Webb imaging data. A small number were new discoveries, appearing in the Ruby's spectra for the first time. And one of those new objects, observed in July of 2024, returned a spectrum so extreme that it effectively halted the analysis. They called it the cliff. Its formal identifier is Ruby's UDS 154183. It sits at a redshift of 3.548, placing it approximately 11.9 billion light-years from Earth. The photons arriving in Webb's detectors from the cliff today began their journey when the universe was only about 2 billion years old, before our Sun existed, before our Earth existed, before any of the stars visible in tonight's sky had formed. The spectrum the cliff returned was the most extreme version of the little red dot signature ever recorded. The V-shape was sharper than in any previously observed example. The Balmer break was nearly vertical, a cliff in the spectrum, which is where the name came from, and almost twice as strong as any equivalent feature previously measured in an object from that era. The broad emission lines were present. The X-ray emission was absent. Every feature that had resisted explanation was there, pushed to its most extreme expression. De Graaf described the team's response directly. The extreme properties of the cliff forced us to go back to the drawing board and come up with entirely new models. That new model took months to work out. It was published in the summer of 2025, and it proposed a structure with no established observational precedent. At the center, a supermassive black hole, actively accreting gas. But the black hole is not sitting at the center of a thin, exposed accretion disk with clear lines of sight, the way it does in a standard quasar. Instead, it is completely enclosed, surrounded on all sides by a thick, dense, roughly spherical envelope of hydrogen gas. The envelope is opaque, not just to visible light, but to the X-rays and hard radiation that would normally escape from the central accretion region. The mass of the envelope is many times the mass of the black hole itself. The envelope is continuously heated from within by the energy released as gas spirals inward onto the central black hole. That energy, released in the intense gravitational field close to the black hole, heats the inner layers of the envelope, which heat the outer layers, which radiate the energy away from the photosphere. The photosphere of the envelope is the effective surface from which light escapes. And the temperature of that surface, set by the balance between the energy flowing outward from the central accretion and the ability of the envelope to radiate it away, settles at around 4,000 Kelvin. 4,000 Kelvin is cool for an astrophysical energy source. It places the peak emission in the red and near-infrared. It is the same temperature range as the outer layers of red giant stars, cool, luminous, evolved stellar objects in their late stages of life. The object, seen from a distance, does not look like a black hole. It looks like an enormous, puffed-out sphere of glowing gas. Like a star. A truly enormous star, hundreds or thousands of times larger than any normal stellar object, but with something fundamentally different hidden inside. The field has converged on a name for this structure, the black hole star. The name is deliberate. It is borrowed from both categories because the object genuinely shares properties with each. In its outward form, a black hole star resembles a stellar object. It has a photosphere, an outer radiating surface like the surface of a star. It is roughly spherical and held up by radiation pressure, as stars are. Its temperature falls at the cool end of the stellar range. In its energy source, however, a black hole star is entirely different from any normal star. A normal star produces energy through nuclear fusion. In its core, the conversion of hydrogen into helium at extreme temperatures and pressures. A black hole star has no fusion. Its energy comes entirely from gravity. Specifically, from the gravitational potential energy released as gas falls inward from the envelope onto the central black hole. As long as there is gas in the envelope to fall inward, the black hole grows and the envelope glows. The structure is, in a sense, a black hole consuming its own cocoon from the inside out. This model resolved the contradictions that had broken every previous explanation. Begin with the missing X-rays. In a standard, active galactic nucleus, X-rays produced close to the black hole travel outward through the relatively transparent accretion disk environment and escape into space. In a black hole star, the black hole is enclosed within a thick, dense, opaque hydrogen envelope. X-rays produced in the accretion region at the center interact with the surrounding gas before they can get out. Hydrogen is an efficient absorber of high-energy radiation, particularly at the temperatures and densities inside a black hole star envelope. The X-rays are absorbed. The gas heats up. The energy is thermalized, distributed across photons at lower individual energies, and re-emitted at optical and infrared wavelengths. That is precisely what we observe. The X-ray luminosity of the central black hole may be enormous. From the outside, it is entirely invisible. The envelope has converted it into something softer. The mass problem dissolved with a more careful analysis of how the spectra were being formed. Recall that the broad emission lines appeared to imply black holes far too massive for their host galaxies. In a standard active galactic nucleus, those lines are broadened by the orbital velocities of gas in the broadline region. In a black hole star, the emission lines are broadened by a combination of orbital velocity and something called electron scattering. As photons travel outward through the dense hydrogen envelope toward the photosphere, they do not travel in straight lines. They scatter repeatedly off free electrons in the gas. Each scattering event can shift the photon's energy slightly. Across a thick, opaque envelope, photons scatter many times before they escape. The cumulative effect of all those scattering events is to broaden any emission line passing through the envelope, adding apparent width beyond what the gas velocity alone would produce. If you use the standard spectroscopic formula, which assumes line width reflects only gas velocity on a line that has been additionally broadened by scattering, you overestimate the true velocity. And, if you use that overestimated velocity to infer black hole mass, you get a mass that is too high, possibly enormously too high, depending on how thick the envelope is. When researchers incorporated the scattering correction into their calculations, the implied black hole masses dropped by orders of magnitude. The black holes fell back within the range permitted by the Magorian relation. The relationship was never being violated. The measurement technique had been failing in an environment it was never designed for. And then the story took a turn that is rare in any branch of science. The model derived from the data, the black hole star, the supermassive black hole enclosed within a dense hydrogen envelope, was not actually new. The core theoretical prediction had been published 16 years before the cliff was observed, in a paper that the field had read, noted, and largely set aside. In July of 2008, Mitchell Begelman, Elena Rossi, and Philip Armitage at the University of Colorado in Boulder submitted a paper to the monthly notices of the Royal Astronomical Society. The title was Quasi-Stars Accreting Black Holes Inside Massive Envelopes. Begelman and his colleagues were not thinking about little red dots. The concept had not been invented. Webb had not launched. They were working on a theoretical problem that had been troubling the field for some time. Supermassive black holes had been found at high redshift. Some had masses of 1 billion solar masses or more, present when the universe was only a few 100 million years old. The standard formation pathway, a massive star collapses and leaves a stellar mass black hole, which then grows by accreting surrounding gas, could not explain this. Even at the theoretical maximum feeding rate, called the Eddington limit, a stellar mass seed cannot grow to 1 billion solar masses in the time available. The Eddington limit is defined by the balance between the radiation pressure from accretion and the gravitational pull on the infalling gas. Specifically, it depends on the ratio between luminosity and mass at the effective radiating surface. In a standard active galactic nucleus, that surface is effectively the inner accretion disk, very close to the black hole itself. Begelman and his colleagues considered what would happen if a black hole formed inside a much larger, denser gas envelope, and if that envelope stayed bound rather than dispersing. In that scenario, the effective radiating surface is not the compact region near the black hole. It is the outer photosphere of the enormous envelope. That surface is vastly larger. The luminosity is spread over a vastly greater area. The radiation pressure per unit area at the actual radiating surface is correspondingly lower. The black hole can therefore accrete at rates far exceeding its own Eddington limit, because the limit calculated at the actual radiating surface is not being violated. The central black hole grows rapidly. The envelope inflates and glows red, held up by the radiation from within. The photospheric temperature of the outer surface settles at around 4,000 Kelvin. The quasi-star persists for a few million years, long enough for the central black hole to grow by substantial factors before the envelope is finally disrupted by the radiation pressure, and the black hole emerges as a standard, active galactic nucleus. Begelman, Rossi, and Armitage worked out the structure, calculated the temperatures, estimated the lifetimes, and published. The paper received citations in subsequent theoretical work on early black hole formation. It was considered a serious and interesting possibility. But without observational evidence, without a telescope capable of detecting quasi-stars at the distances where they should exist, it remained theoretical. 16 years passed. The James Webb Space Telescope launched, deployed, and began producing data. The little red dots appeared. Astronomers spent 2 years studying them, ruling out every standard explanation, and were forced toward a model in which supermassive black holes sat inside dense hydrogen envelopes, glowing red, with photospheres around 4,000 Kelvin, invisible in the X-rays, with emission lines broadened by scattering through the envelope. The 2008 paper described these objects with near-exact accuracy. The compactness of the objects, because the envelope, though large by stellar standards, is tiny compared to any galaxy. The redness, because the photospheric temperature of 4,000 Kelvin places the peak emissions squarely in the red and near-infrared. The sharp Balmer break produced by the hydrogen envelope absorbing and processing radiation from within, rather than by dust reddening. The absence of detectable X-rays absorbed by the opaque envelope before they can escape. The temperature signature, consistent with a hydrogen photosphere at the temperature Begelman had calculated. The broad emission lines that had appeared to imply impossibly massive black holes, now understood as partly a product of scattering through the envelope. The match is not perfect. There are details in the observations that require modifications to the 2008 model. The original theoretical paper was an exploration that could not anticipate every observational feature. Refinements are ongoing. But the core prediction, a black hole growing inside a dense hydrogen envelope, producing a glowing, red, star-like photosphere at around 4,000 Kelvin, is exactly what the Ruby's data shows. Begelman, Rossi, and Armitage described these objects in theoretical detail more than a decade before anyone could observe them. When the observations arrived, the prediction was waiting. There is a reason this matters beyond the immediate solution to a specific observational puzzle. Supermassive black holes are not exotic rarities. They are central features of the universe we live in. They sit at the cores of nearly every large galaxy that has ever been studied in detail. Sagittarius A, the black hole at the center of the Milky Way, has a mass of roughly 4 million solar masses. The black hole at the center of M87, the first black hole ever directly imaged by the Event Horizon Telescope in 2019, has a mass of approximately 6.5 billion solar masses. The most massive black holes ever measured exceed 10 billion solar masses, residing at the cores of the largest elliptical galaxies in the universe. These objects shape their host galaxies in fundamental ways. When they are actively accreting gas, the radiation and winds they produce can heat the surrounding interstellar medium, suppress star formation, regulate the growth of the host galaxy, and drive large-scale outflows of gas. The co-evolution of galaxies and their central black holes, the feedback processes that link the two together and maintain the Magorian relation, is one of the central themes of modern astrophysics. And yet the origin of those black holes, particularly how they grew so massive so quickly in the early universe, has been among the most persistent and unresolved problems in the field for 20 years. The standard formation pathway produces seeds far too small. Even running at the Eddington limit continuously, those seeds cannot reach the observed masses within the available time. Something else was happening. The quasi-star model offers a route through that gap. If the earliest black holes grew through a quasi-star phase embedded within dense, primordial hydrogen envelopes, feeding at super-Eddington rates for a few million years before their envelopes dispersed, then the numbers become feasible. Small seeds could reach supermassive status within the time constraints imposed by the high redshift observations. The little red dots may be that growth phase, caught in the act for the first time. Before Webb, this phase was invisible to us. Too long ago, too faint, too infrared. No instrument we had built could see it. Now, one can. And what it sees is not a slow, gradual, orderly process of black hole assembly stretching across billions of years. It is rapid, violent, and obscured a brief period of explosive growth inside hydrogen envelopes, lasting only a few million years in any given location, producing objects unlike anything in the modern universe, and leaving behind the seeds of the supermassive black holes that now anchor every large galaxy in the observable cosmos. The quasi-star phase ends. Black hole stars are transient objects, brief, intense episodes in the lives of their central black holes. As the central black hole feeds on the surrounding envelope, the energy output from the central accretion increases. The envelope is gradually consumed. Begelman's original analysis identified a critical threshold. When the photospheric temperature of the envelope drops below roughly 4,000 Kelvin, the outer layers can no longer absorb the radiation efficiently enough to remain supported. The balance between radiation pressure and gravity breaks down. The outer layers collapse inward and then are driven outward by the radiation from within. The envelope disperses. The black hole emerges from its cocoon. No longer hidden, no longer embedded within a dense hydrogen shell. The object transitions from a black hole star dim in X-rays, red in color, stellar in appearance, into a standard active galactic nucleus, with a visible accretion disk glowing in multiple wavelengths, and X-ray emission now escaping freely. The timing is consistent with the observations. The little red dot population is concentrated in the era from roughly 500 million to 1 billion years after the Big Bang. It drops off after that. The objects do not disappear. They evolve. Their envelopes disperse. Their central black holes continue. The most luminous quasars known in the early universe, objects with hundreds of millions to billions of solar masses, discovered in large numbers by surveys going back decades, may be the direct descendants of the little red dots. The black holes, growing obscured within hydrogen envelopes in the first billion years of cosmic history, emerge, a few 100 million years later, as the most powerful beacons in the early universe. We have been cataloging the descendants for decades. We can now for the first time, see their precursors. The story is not finished. Many open questions remain. The exact mechanism by which the initial hydrogen envelopes form around the black hole's seeds is not fully established. Whether all supermassive black holes pass through a quasi-star phase or only a subset remains uncertain. How the duration of the quasi-star phase varies with the mass and environment of the initial seeds has not been fully worked out. Whether the conditions that produce little red dots are unique to the very early universe or can occur at later times in the right environments is an active area of theoretical investigation. The details of the transition from quasi-star to standard active galactic nucleus, whether it is sudden or gradual, whether it leaves traces in the surrounding medium that we might one day observe, are being worked through in new theoretical and simulation-based studies. And there are observational features in some of the little red dots that the current quasi-star framework does not yet fully account for. Details in the spectra that hint at additional physics. Layers of the story that have not yet been fully read. Papers are appearing at a remarkable rate. The field is moving faster on this topic than on almost any other in observational cosmology. Each new paper adds precision, challenges assumptions, or proposes modifications to the quasi-star interpretation. The picture is sharpening. It is not finished. What the quasi-star model has accomplished is to account for more of the observational data with fewer additional assumptions than any alternative that has been proposed. It explains the redness, the compactness, the Balmer break, the absence of X-rays, and when the scattering effect in the envelope is properly incorporated, the apparent black hole masses. It is the current, leading explanation. It is not the final word. The next decade of observations will put it under increasing pressure. More surveys with Webb are being planned. The Nancy Grace Roman Space Telescope, currently in development at NASA, will survey vastly larger areas of sky to infrared depths comparable to Webb's deepest fields, potentially finding little red dots in numbers, orders of magnitude larger than current catalogues. Greater statistical power will reveal the population's true distribution and test whether the quasi-star model's predictions hold across the full range of observed properties. New X-ray observatories with greater sensitivity will probe the hard radiation environments of these objects in more detail, testing whether the envelope absorption explanation accounts for the full range of observed X-ray non-detections. Theoretical work will refine the quasi-star model with more detailed physics, including the gas dynamics of the envelope, the growth rate of the central black hole under different conditions, and the physical triggers that determine when the transition to an active galactic nucleus occurs. The picture will sharpen. New questions will emerge that the current framework has not yet anticipated. That is how science advances. Not in straight lines toward predetermined answers, but in an iterative process of observation, modeling, prediction, and revision. Each step adds something real to the sum of what we know, even when, especially, when it reveals how much we still don't. Before Webb, the first billion years of the universe was a chapter we could sketch only in outline. We knew the general sequence: dark ages, first stars, first galaxies, gradual assembly of structure. We knew the endpoint, the richly structured cosmos of galaxies, black holes, and large-scale filaments we observe today. But the details of the transition, especially the question of how the most massive black holes bootstrap themselves into existence so rapidly, remained genuinely unsolved. The little red dots are the first direct observational window into that transition. They reveal a phase of cosmic history that had been completely hidden before Webb opened its infrared eyes on the early universe. A phase of rapid, obscured, vigorous black hole growth. A phase lasting only a few million years in any given location, brief beyond reckoning in cosmic terms. But a phase that may have seeded the supermassive black holes sitting at the centers of every large galaxy in the observable universe. The discovery changed something fundamental about the story we tell. Not just a detail or a calibration. A chapter. A chapter that was missing from the very beginning of the narrative. And it arrived wrapped in one of the more remarkable coincidences in recent scientific history. A theoretical prediction from 2008, describing in quantitative detail the physical structure of objects that would not be observed for 16 years, matched those objects when they were finally found. The theorists wrote down what the universe was doing in a place and at a time no instrument could yet see. The universe had been encoding the same answer into the light of these objects for nearly 12 billion years. That light was already traveling through space in 2008. It had been traveling for almost the entire age of the cosmos, carrying information that Beegelman and his colleagues had, through careful theoretical physics, predicted correctly. Webb caught it. And when the spectra came back from the cliff, and from 1,000 other little red dots scattered across the deepest images of the early universe, both descriptions, the theoretical one, written in 2008, and the observational one, written in photons 12 billion years ago, said the same thing. A black hole, inside a dense cloud of hydrogen gas, growing rapidly in the dark, glowing red from the outside, invisible in the X-rays, waiting to be found. That is what the little red dots are, objects that existed all along, going about their brief, intense lives in the earliest layers of the observable universe. Objects whose light has been traveling toward us since before our solar system existed. Objects that 3 theorists in Colorado described in mathematical terms 16 years before anyone could prove they were real. The universe had been writing the same answer from 2 different directions the whole time. We needed the right instrument to read it. That instrument has been built. The significance of the quasi-star discovery extends well beyond the specific physics of the little red dots. It speaks to something deeper about the way the universe built itself, and the way science works when it tries to reconstruct that process from incomplete evidence. We observe the universe across a vast range of cosmic time, but we do not observe it continuously. We observe snapshots. Light from different distances reaches us from different eras, and what we can resolve within those eras depends entirely on the capabilities of the instruments we have. Before Webb, the era from 500 million to 1 billion years after the Big Bang was accessible to us only in the broadest strokes. We could detect the existence of galaxies at those redshifts. We could make rough estimates of their masses and star formation rates. But the resolution and sensitivity required to study individual objects in detail, to take spectra that could distinguish between a starburst galaxy and a quasi-star, was simply beyond what any telescope before Webb could provide. The gap in our observational coverage was not a gap in the universe's history. The universe continued operating in that epoch, whether or not we could see it clearly. Galaxies were forming. Stars were igniting. Black holes were growing. The quasi-stars were glowing for their few million years of existence, flooding the surrounding intergalactic medium with red light. All of that was happening. We just could not see it at the resolution needed to understand what it meant. Webb changed that. It did not reveal a new part of the universe. It revealed a part of the universe that had been there all along, but had been effectively invisible to every previous generation of astronomers. The little red dots are the clearest demonstration of that change. They were present in the sky, in principle detectable, but only at wavelengths and at sensitivity levels that Hubble could not reach. Webb could. And what it found there, in that previously inaccessible window, was not what anyone had predicted would be there. Not because the predictions were careless, because they were based on the best available models, and those models had been validated against every observation that existed before Webb. The models were right about everything they could be tested against. They were wrong about something they had never been tested against. That is not a failure of science. That is exactly how science is supposed to work. One of the things the Little Red Dot story reveals is how the architecture of scientific knowledge shapes what can be discovered and when. The quasi-star prediction, made by Begelman, Rossi, and Armitage in 2008, was not a wild speculation. It was a well-motivated theoretical inference, built from solid principles of general relativity, radiation, hydrodynamics, and stellar structure theory. The authors worked through the physics carefully. They calculated the properties of the object they were predicting. They made specific, quantitative predictions: the temperature of the photosphere, the luminosity of the object, the timescale of the quasi-star phase. All of those predictions were, in principle, testable. But they were not testable with any instrument that existed in 2008. The objects were predicted to exist at redshifts corresponding to the very early universe. They were predicted to have spectral signatures in the infrared. Infrared observations at the sensitivity and resolution required were not technically possible until Webb. So the prediction sat in the literature, cited occasionally in theoretical papers on early black hole growth, but unable to interact with observational data in any productive way. The sociology of science has a phrase for this kind of situation. It is called a theoretical prediction waiting for an instrument. There are many such predictions in astrophysics. Some are confirmed when the right instrument eventually arrives. Some are not. Some are confirmed in modified forms that differ in important ways from the original prediction. The quasi-star prediction was confirmed in a way that surprised even the people who had been working on the little red dots most intensively. Not because anyone had been looking for quasi-stars specifically, but because the properties of the objects they were observing, when the data was analyzed carefully, kept pointing toward a structure that matched the 2008 paper. The paper was not famous. It was not widely cited outside of the narrow theoretical community working on early black hole formation. Most of the astronomers who first catalogued and studied the little red dots were not thinking about quasi-stars at all. They were thinking about starburst galaxies and active galactic nuclei, the two categories that seemed most plausible given the initial observations. The 2008 paper was rediscovered, in a sense, by necessity. When both of those categories failed, when the data kept producing results that fit neither standard explanation, researchers started searching the literature for alternatives. And there it was. A 16-year-old paper describing a class of object whose properties matched the little red dots in almost every quantitative detail. That is a genuinely unusual sequence of events in modern astrophysics. A theoretical prediction made without any observational motivation, made purely as a solution to a different theoretical problem that turned out to describe a real population of objects. Discovered by a different telescope, working on different questions more than a decade later. It is the kind of thing that does not happen often. And when it does happen, it suggests something important about the universality of the physical principles involved. Begelman and his colleagues were not trying to predict what Webb would find. They were trying to solve a problem about how supermassive black holes could grow fast enough in the early universe. The solution they found, a black hole feeding inside a dense gas envelope, was physically robust enough that it described real objects that the universe had actually produced. The universe was, in a sense, solving the same problem. It needed a mechanism for rapidly growing supermassive black holes in the first billion years. The quasi-star mechanism was its solution. Begelman described that solution theoretically. Webb found it observationally. The match was not a coincidence in any deep sense. It was a consequence of both the universe and the theorists following the same underlying physics to its natural conclusion. The scientific community's response to the little red dots has moved through stages that are recognizable in the history of any major discovery. The initial reaction in 2022 and early 2023 was cautious excitement. The objects were real. They were abundant. They were unusual. But initial measurements were uncertain. Redshift estimates could be wrong. Photometric measurements could be misinterpreted. The sensible response was to gather more data before drawing strong conclusions. The next stage, through 2023, was the building of competing hypotheses. The starburst galaxy model and the active galactic nucleus model were both developed, refined, and tested against the growing dataset. Both were taken seriously. Both had genuine observational support. The field did what it is supposed to do when multiple hypotheses compete. It collected more data, designed specific tests to distinguish between them, and followed the evidence. The evidence, by late 2024, had eliminated both standard models. The response to that elimination, rather than forcing the data into one of the existing categories or treating the anomalies as measurement errors, was to accept that the objects were genuinely novel and that a new framework was required. That acceptance is not as easy as it sounds. In any scientific field, there is institutional momentum behind established frameworks. Models that have been tested and validated accumulate authority. Departing from them requires not just compelling evidence, but also a willingness to accept uncertainty, to say, this is a real effect, we do not understand it, and our existing categories are inadequate. That willingness, in the case of the little red dots, was present. The community engaged seriously with the problem, explored the alternatives, and arrived at the quasi-star model not because it was comfortable or familiar, but because it was the explanation most consistent with the full body of available evidence. That is the scientific process working as it should. Slowly, sometimes painfully, but ultimately oriented toward the most accurate description of what the universe is actually doing. It is worth spending a moment on the physics of the Eddington limit, because understanding it is essential to understanding why the quasi-star mechanism matters for the problem of early black hole growth. The Eddington limit is named for Arthur Eddington, the British astrophysicist who derived it in the early 20th century. It defines the maximum luminosity that a gravitating object of a given mass can radiate. If the radiation is in equilibrium with the gravity that holds the surrounding gas in place. The logic is as follows. When a black hole or any compact object accretes gas, the gas falls inward and releases energy as radiation. That radiation exerts pressure on the surrounding gas through the process of photon absorption and scattering. The radiation pressure pushes the gas outward. The gravity of the central object pulls it inward. When the radiation is powerful enough, the outward pressure of the radiation exactly balances the inward pull of gravity. Beyond that point, additional luminosity would push the gas away faster than gravity can pull it back, and the accretion shuts off. This balance defines the Eddington luminosity, the maximum luminosity for a given mass, and the corresponding maximum accretion rate, called the Eddington accretion rate. The Eddington limit is not a hard physical barrier in all circumstances, but it is a well-tested and generally applicable constraint. For a stellar mass black hole of a few solar masses, the Eddington accretion rate allows it to double its mass on a timescale of roughly 45 million years if it accretes continuously at the maximum rate. Starting from a seed of a few solar masses and wanting to reach 1 billion solar masses in, say, 800 million years, the age of the universe at the redshifts of the most distant known quasars requires continuous Eddington accretion with essentially no interruption. That is a constraint most realistic accretion scenarios have difficulty satisfying. Accretion is not continuous. It depends on the availability of cold, dense gas near the black hole. Feedback from the accretion itself heats the surrounding gas, reducing the supply of cold fuel. Mergers and other dynamical processes interrupt the supply. The problem of growing supermassive black holes in the early universe in the required time, given these constraints, is genuinely difficult. The quasi-star mechanism bypasses the constraint in an elegant way. By embedding the black hole within a dense envelope whose outer surface is the effective radiating surface, the calculation of the Eddington limit shifts. The relevant mass in the Eddington limit calculation becomes not the mass of the black hole, but the mass of the entire system, the black hole plus the envelope. And the relevant luminosity is the luminosity of the photosphere, spread over the large surface area of the envelope. The result is that the black hole can accrete at rates far exceeding its own Eddington limit, while the photosphere of the envelope remains below its Eddington limit. The black hole grows rapidly. The envelope glows. And the growth continues until the envelope is consumed or dispersed. This is not a violation of any physical principle. The Eddington limit is a constraint on the luminosity of the radiating surface, not directly on the accretion rate of the central object within an opaque environment. In the appropriate physical context, a black hole embedded within a dense, opaque gas envelope, the limit calculated at the black hole's surface differs from the limit calculated at the photosphere. The quasi-star exploits this difference. And in doing so, it solves the timeline problem for early supermassive black hole growth in a way that earlier theoretical models had not anticipated. Understanding the structure of the black hole star in a little more detail helps clarify why it looks the way it does to our telescopes, and why every observable feature points toward this interpretation rather than any alternative. Consider what happens to a photon emitted in the central accretion region near the black hole. It has been produced at high-energy X-ray or even gamma-ray energy by the hot, compressed gas spiraling into the black hole. It starts traveling outward. Almost immediately, it encounters the dense hydrogen gas of the inner envelope. Hydrogen gas, at the temperatures and densities of the black hole star's interior, is largely ionized. The electrons have been stripped from the protons by the intense radiation. Ionized hydrogen contains free electrons that are extremely efficient at scattering photons. This process is called Thomson scattering or electron scattering. Every photon traveling outward through the envelope encounters free electrons and is scattered in a new direction. It does not travel in a straight line outward. It follows a random walk scattered one way, then another, gradually diffusing outward through the envelope over a time scale that depends on the density and thickness of the gas. During that random walk, the photon's energy gradually shifts. Each scattering event exchanges energy between the photon and the surrounding gas. If the gas is cooler than the photon's energy would imply, the photon loses energy to the gas. Over many scattering events, the photon's energy is thermalized. It comes into equilibrium with the local gas temperature. By the time the photon reaches the photosphere, the outer surface of the envelope from which radiation can finally escape freely, it has been thoroughly processed. It no longer carries the specific energy of its origin near the black hole. It carries the energy corresponding to the temperature of the photosphere, around 4,000 Kelvin. At 4,000 Kelvin, the peak of the emission spectrum falls in the red and near-infrared. The photosphere radiates as a body at 4,000 Kelvin, a cool red glow. This is why the little red dots are red. Not because they are covered in dust, not because their stars are old and cool, but because they are black hole stars and their photospheric temperature is set by the physics of the hydrogen envelope and the accretion luminosity within. The redness is a direct signature of the quasi-star structure. Similarly, the sharp Balmer break in the spectra is a direct consequence of the hydrogen composition of the envelope. Hydrogen, at the right temperature and density, produces a pronounced absorption edge at the Balmer limit wavelength. In a black hole star, the outer layers of the envelope are at just the right temperature to produce this absorption efficiently. The break is not produced by stars or by dust. It is produced by the hydrogen photosphere itself. Everything about the spectral appearance of the little red dots, when interpreted in the context of the quasi-star model, points to a hydrogen envelope heated from within. The color, the break, the absence of X-rays, the broad emission lines. Each feature that had been a puzzle under the standard models becomes a natural prediction of the quasi-star framework. The implications for galaxy formation extend beyond the question of black hole seeds. If the little red dots are quasi-stars, and if quasi-stars represent a common or universal phase in the early growth of supermassive black holes, then the feedback effects of that phase need to be incorporated into models of early galaxy formation. Active black holes, standard active galactic nuclei and quasars are known to be powerful agents of feedback in their host galaxies. They heat and drive away the surrounding gas, suppressing star formation. They can drive large-scale outflows that reshape the interstellar medium. They inject energy and momentum into the circumgalactic medium on scales extending hundreds of thousands of light-years beyond the galaxy itself. The feedback from active galactic nuclei is considered one of the key regulatory processes in galaxy evolution, a major reason why the most massive galaxies in the universe stopped forming stars long ago. If quasi-stars represent a phase before the standard active galactic nucleus phase, then the feedback from quasi-stars is also early feedback, feedback operating in the first billion years of the universe, potentially shaping the galaxies that would eventually host the first visible quasars. The details of that feedback are different from standard active galactic nucleus feedback. The radiation from a quasi-star is thermalized within the envelope and emerges as optical and infrared light rather than X-rays and ultraviolet. The effect on the surrounding gas is therefore different. How different, and what the consequences for early galaxy formation are, is currently an active area of theoretical work. These are not questions that can be answered easily from the current observational data alone. They require a combination of new observations, deeper, higher resolution spectroscopy of the little red dots and their surroundings, and new theoretical modeling that incorporates the quasi-star phase into full cosmological simulations of galaxy formation. Both of those efforts are underway. The next few years will see a significant expansion of our understanding of this early epoch. But the direction the field has taken from confusion and failed models to the quasi-star interpretation suggests that the picture is now correctly framed. The remaining questions are about the details. The broad structure is becoming clear. There is one more dimension to the little red dot story that deserves attention, because it connects the specific astrophysical discovery to a broader pattern in the history of astronomy. Astronomy is, in its essence, the science of looking at things we cannot touch, cannot visit, and cannot directly manipulate. Everything we know about objects beyond our own solar system, and most of what we know about objects within it at remote scales, comes from analyzing light. Different wavelengths of light. Light collected over different timescales. Light interpreted through the frameworks of physics that we have developed and tested here on Earth. The power of that approach is enormous. From the light alone, we can determine the temperature, composition, motion, age, mass, and energy output of objects billions of light years away. But the limitation is equally significant. We can only ever see what our instruments can detect. We can only ever understand what our theoretical frameworks can interpret. When the instruments improve, as they did when Webb launched, we gain access to information that was previously unavailable. Sometimes, that new information fits neatly into the existing picture. Sometimes it does not. The little red dots did not fit. They revealed that the existing picture, one of the most carefully constructed and thoroughly tested frameworks in all of science, was missing a chapter. Not wrong. Missing. The chapter it was missing is now being written. The instruments that will write the subsequent chapters are already being designed and built. The Nancy Grace Roman Space Telescope, named for NASA's first chief of astronomy, will survey thousands of square degrees of sky at infrared sensitivities approaching those of Webb's deepest pointed observations. Where Webb has found thousands of little red dots by staring at small patches of sky for many hours, Roman will find them across large fractions of the sky, building samples large enough to characterize the population statistically in ways the current data does not permit. The extremely large telescope, currently under construction in Chile, with a primary mirror 39 meters across, will be able to collect follow-up spectra of individual little red dots at resolution and signal-to-noise ratios that Webb cannot match. Future X-ray observatories, proposed and under development, will probe the hard radiation environments of these objects with sensitivity far beyond Chandra and XMM Newton. Each of these instruments will add something to the picture. Each will resolve some of the remaining uncertainties. And each will almost certainly reveal new puzzles that the current framework has not anticipated. That is the nature of progress at the frontiers of observational astrophysics. The frontier moves. The instruments improve. The picture deepens. And periodically, not often, but occasionally, something is found that requires not just a refinement of the existing picture, but a genuine revision of one of its foundational assumptions. The little red dots have done that. They have forced a revision of our understanding of how supermassive black holes grow in the early universe. They have connected a forgotten theoretical prediction to a set of observations that no one was expecting. And they have opened a window into a phase of cosmic history that, until a few years ago, was genuinely invisible to us. That window is now open. What we see through it is still coming into focus. But the outlines are clear enough to say, with some confidence, that the universe in its first billion years was doing something we did not fully understand before. Something rapid. Something obscured. Something that left its mark on every large galaxy in the observable universe. And something that, as of 2026, we are for the first time beginning to properly see. The light from the little red dots has been traveling toward us for nearly 12 billion years. It carries the signature of a process we did not know existed. A phase of black hole growth that was brief, intense, and hidden within dense clouds of hydrogen gas in the earliest period of the universe's structured history. That light arrived at Webb's mirror after a journey of almost incomprehensible length, and what it revealed, encoded in the pattern of its wavelengths, was a story that had been written by the universe itself long before any human was alive to wonder about it. In 2008, 3 physicists at a university in Colorado sat down with equations and asked, what would happen if a black hole formed inside a dense gas cloud and the cloud stayed bound? They worked through the physics. They wrote down the answer. They described a red, compact, star-like object with a hydrogen photosphere, a temperature near 4,000 Kelvin, and a central black hole growing faster than any standard model allowed. They published the paper. The objects they described were already out there in the universe, shining their red light into space. The telescope that would eventually capture that light would not launch for another 13 years. The astronomers who would eventually recognize what that light meant would spend 2 years, ruled out every other explanation before the 2008 paper resurfaced. And when it did, the match between theory and observation was close enough to stop the analysis in its tracks. The universe had written the answer in light 12 billion years ago. The theorists had written the same answer in equations 16 years before it could be read. Webb gave us the eyes to read both. What we read was not a story of a universe behaving as expected. It was the story of a universe building its most massive structures through a process faster, more violent, and more hidden than our models had imagined. A process that left its fingerprints on every supermassive black hole in every large galaxy that has ever existed. A process we are only now beginning to see clearly. The little red dots were there all along. We just needed the right eyes. Sitting with all of this, the discovery, the failed hypotheses, the forgotten prediction, the instrument that finally made it visible, it is worth reflecting on something that often gets lost in the technical details of any major scientific advance. The little red dots are not just an astrophysical puzzle. They are a window into one of the most fundamental questions any conscious being can ask. Where did the structures of the universe come from? not the philosophical question of why there is something rather than nothing. The practical, scientific question of how a cosmos that began as a nearly featureless plasma of hydrogen and helium produced, within a billion years, the complex, diverse, richly structured universe we observe today. Galaxies, stars, planets, black holes, clusters, filaments. Voids, a universe of extraordinary complexity assembled from simple initial conditions in a relatively short time. The process by which that assembly happened is, in a deep sense, the history of everything. The little red dots are a piece of that history that was hidden, a phase that could not be seen until a specific technological threshold was crossed, a threshold that took decades and billions of dollars to cross, and that, once crossed, revealed something genuinely unexpected. The quasi-stars are part of the answer to how the universe got its current structure. They are the hidden growth phase of the most massive black holes. And those black holes are, in turn, fundamental to the existence of the galaxies we observe today. The feedback from active galactic nuclei, the jets, the winds, the radiation that heats and expels gas from galaxies is one of the key regulatory processes that shaped which galaxies grew large and which remained small. Without the growth of supermassive black holes, the galaxy population would look very different. The universe as we know it, with the mix of galaxy types, masses, and star formation histories that we observe, depends in important ways on the specific history of black hole growth in the early universe. That history now includes the quasi-star phase, the hidden chapter in the story of cosmic structure. The discovery also raises a question that is difficult to answer but worth asking. If the quasi-star phase was invisible before Webb, what other phases of cosmic evolution might still be invisible to us? What other processes, operating at wavelengths or distances or timescales beyond our current observational reach, are shaping the universe in ways we have not yet detected? The history of astronomy is a repeated demonstration that the accessible universe is smaller than the actual universe. Every time we extend our observational reach in wavelength, in sensitivity, in angular resolution, in time baseline, we find things that were there all along, but invisible to previous instruments. The radio universe revealed jets, pulsars, and the cosmic microwave background. The X-ray universe revealed the violent, hot gas-filling clusters of galaxies. The infrared universe, accessible from space, revealed star-forming regions hidden behind dust clouds and the light of the earliest galaxies. The gravitational wave universe, opened by LIGO in 2015, revealed the merger rates and mass distributions of black holes and neutron stars in a way that optical astronomy had never been able to access. Each new window revealed not just new objects, but new processes, new chapters in the story of how the universe works. Webb opened a new window, and in the first years of looking through it, it found something that required revising one of the foundational assumptions of galaxy formation theory. The implication is clear. The universe is not done surprising us. Every expansion of our observational reach will encounter something we did not anticipate. The question is not whether there are more hidden chapters. There certainly are. The question is when the next instrument will be built that is capable of revealing them. The James Webb Space Telescope is, right now, in the early years of what will likely be a productive scientific career of many decades. Its mirror, its instruments, and its orbital position are all expected to remain functional well into the 2030s. In those years, it will continue to characterize the little red dots in greater detail. It will observe more of them. It will take deeper, higher resolution spectra that will reveal additional features of their structure. It will follow up on the most extreme examples, objects like the cliff, with pointed observations designed to isolate specific spectral features that can distinguish between competing models. The quasi-star interpretation will be tested in detail. Its predictions will be compared against new data. The parts that are correct will be confirmed. The parts that are wrong or incomplete will be revised. And through that process, the understanding of the quasi-star phase will deepen from its current state, a qualitatively compelling but quantitatively incomplete picture, into a rigorous, well-tested model with specific predictive power. That is the scientific process on its normal timescale. Not a sudden revelation, but a gradual accumulation of evidence and understanding. The little red dots will remain scientifically active objects for years. They will not be solved in a single paper or a single year. They will be understood progressively through the combined work of many research groups using many different instruments and techniques. That is how astronomy advances. And the direction it is advancing, in the case of the little red dots, is toward a clearer picture of the universe's earliest and most vigorous phase of black hole growth. A phase that was hidden for billions of years. A phase that 3 theorists predicted in 2008. A phase that Webb found, in the form of hundreds of tiny red points of light scattered across the deepest images of the observable universe. The little red dots were always there, glowing their red glow, hiding their black holes, waiting for the right eyes. Now we have them. There is a particular quality to the moment in science when a long-standing theoretical prediction meets observational confirmation for the first time. It is different from the more common experience of a hypothesis being tested and confirmed. In those cases, the theorist and the observer are usually aware of each other. Working in an active dialogue, the theorist makes a prediction, the observer designs an experiment. The result comes back, and the prediction either stands or falls. The quasi-star case was not like that. Begelman's prediction was not made in anticipation of Webb. De Graaff's observations were not designed to test the quasi-star model. The connection was made only after the fact, when the data was already in hand and every standard explanation had been exhausted. It is the kind of connection that requires both parties, the theoretical prediction and the observational data, to be ready at the same moment, and for someone to have the breadth of knowledge to recognize the match. That recognition is itself a scientific skill, undervalued in an era that tends to focus on the discovery moment rather than the synthesis moment. The synthesis moment, when 2 previously unconnected pieces of work are seen to describe the same thing, is often where the real advance in understanding happens. The prediction tells you what the physics implies. The observation tells you what the universe actually does. When they agree, something genuinely important has been learned. Not just that this particular object has these particular properties, but that the physical principles underlying the prediction are correct in ways that extend beyond any single object. The fact that the quasi-star model, derived from general principles of radiation, hydrodynamics, and accretion physics, describes the little red dots accurately means that those principles apply in the early universe in the way they apply locally. The laws of physics are universal. That is, in a sense, the most important lesson that every astrophysical discovery teaches. The laws of physics do not change with time or place. The same equations that govern the behavior of gas falling onto a black hole in a laboratory simulation govern the behavior of gas falling onto a black hole 12 billion light-years away. 12 billion years ago. The universe is a consistent system. It follows the same rules everywhere. And because it follows the same rules, a prediction made from first principles in a university office in Colorado in 2008 can describe objects at the edge of the observable universe with quantitative accuracy. That consistency, that universality, is what makes science possible across cosmic distances and cosmic time. It is, when you sit with it, one of the more astonishing features of the universe we live in. The little red dots emerged from a specific combination of circumstances that is worth tracing. They were found because Webb was built. Webb was built because of a sustained, multi-generational commitment to infrared space astronomy that began in the 1980s with the IRAS satellite, continued through the Spitzer Space Telescope, and reached its culmination in the scale and ambition of Webb itself. Each step in that progression produced scientific results, refined engineering approaches, and built the community of scientists and engineers who knew how to design, build, and operate infrared space observatories. The quasi-star prediction was found in the literature because researchers working on the little red dots were thorough enough and knowledgeable enough to search through decades of theoretical work when the standard explanations failed. The data that broke the standard explanations was produced by a combination of Webb's unique capabilities and the design of surveys, like Ruby's surveys, that prioritized spectroscopy, that collected large enough samples to identify statistical patterns, and that were willing to invest, observing time in objects that were puzzling rather than objects whose nature was already understood. The recognition that the quasi-star model fit the data was the product of careful theoretical analysis by a team that was willing to go back to the drawing board when the existing frameworks failed. None of these things happened automatically. They were the result of choices made by funding agencies about which instruments to build, choices made by scientists about which observations to prioritize, choices made by individuals about how deeply to search and how rigorously to test. The discovery of the little red dots and their connection to the quasi-star model is a human story as much as it is a scientific one. It required the sustained effort of thousands of people over decades. Engineers who built the instruments, scientists who designed the surveys, analysts who processed the data, theorists who built the models, and editors and reviewers who tested the conclusions before they were published. The result of all that effort is a discovery that changes our understanding of how the universe built its most massive structures in the first billion years. That seems like a reasonable return on the investment. There is one more thing worth noting about the little red dots, and it concerns the size of the sample and what it implies about the quasi-star phase more broadly. By early 2026, more than 1,000 little red dots had been catalogued. They are present in roughly 1 in every 100 objects at the relevant redshifts in the deepest Webb fields. That is a substantial number. It implies that the quasi-star phase, if that is what the little red dots represent, was not a rare exception in the early universe. It was a common occurrence. If roughly 1% of all objects at those redshifts are quasi-stars, and if each quasi-star harbors a rapidly growing supermassive black hole, then the early universe was populated with actively growing black holes in enormous numbers. The total number of quasi-stars that existed in the observable universe during the epoch from 500 million to 1 billion years after the Big Bang is difficult to estimate precisely, but it is certainly in the billions. Each of those quasi-stars was growing a black hole that would eventually anchor a galaxy. The galaxy population we observe today, hundreds of billions of galaxies, each with a central black hole, traces its black hole content, in part, to that early phase of quasi-star growth. The population of little red dots we are observing with Webb is a sample of that broader phenomenon. A snapshot, in a specific range of redshifts and luminosities, of a process that was operating across the entire early universe. The quantitative study of that population, its mass function, its luminosity function, its redshift distribution, its clustering properties will be one of the central scientific products of Webb's extended mission. Roman will expand the sample dramatically. And from those expanded samples, the quasi-star phase will be characterized not just qualitatively, but quantitatively. How long it lasted on average, how rapidly the black holes within grew, how the duration and growth rate depended on the initial conditions of the envelope. These are not questions that can be answered with the current data. They are questions that the next generation of observations is positioned to address. And when they are answered, we will have a much more complete understanding of the early black hole growth history of the universe, and through that, a more complete understanding of why the universe of galaxies and structures that we observe today looks the way it does. The little red dots are small. The questions they raise are large. And the answers, when they come, will be among the most significant advances in our understanding of the cosmos, since the discovery that galaxies are island universes beyond the Milky Way. The universe does not announce its surprises in advance. It simply continues operating, following its laws, producing its structures, running its processes on timescales that are indifferent to whether any conscious observer is watching. The quasi-stars glowed their red glow for a few million years each in the first billion years of cosmic history. And then their envelopes dispersed, and their black holes moved on to the next phase of their existence. The light from those quasi-stars traveled outward into space in all directions. A tiny fraction of it traveled in our direction. For nearly 12 billion years, it traveled across an expanding universe, stretching to longer wavelengths as it went, until it arrived at a mirror made of 18 gold-coated beryllium segments floating at the second Lagrange point of the Earth-Sun system. Webb collected it. Spectrographs dispersed it by wavelength. Detectors measured how much light was present at each wavelength. Software converted those measurements into numbers. Scientists examined those numbers and found something they did not expect. That sequence from the quasi-star glowing in the early universe to the scientist staring at an unexpected spectrum on a computer screen is the story of astronomy. Not a story about instruments or techniques, though instruments and techniques are how it is done. A story about the universe, revealing itself to creatures that evolved within it. Creatures who developed tools, mathematics, and physical intuition powerful enough to read the messages that the cosmos has been sending out for billions of years. The little red dots are one of those messages, sent 12 billion years ago, delivered to our instruments in the last few years. Read, incompletely but increasingly clearly, by the community of scientists who study the early universe. The message says, the universe grew its most massive black holes faster and more strangely than you thought. There was a hidden phase. A phase of rapid, obscured growth inside hydrogen envelopes. A phase that lasted a few million years and left behind the seeds of every supermassive black hole in every large galaxy you can see. You missed it before. Now you can see it. Look more carefully. There is more to find. Every discovery in astrophysics is also a reminder of how much time separates what we observe from when it happened. The little red dots we are studying today are not objects that exist now. They are objects that existed billions of years ago. The light we collect from them is historical light, ancient light. Light that has been in transit for a span of time longer than the age of our solar system. When we study the little red dots, we are not looking at a part of the universe as it currently is. We are looking at a fossil record, a preserved image of a process that concluded billions of years ago. Its products, now distributed throughout the modern universe in a form entirely unrecognizable from the red, compact points of light Webb captures in its deepest fields. The quasi-stars that Webb observes today, if they are correctly identified, no longer exist. They existed, briefly, in the first billion years after the Big Bang. Their envelopes dispersed. Their central black holes emerged and became quasars. The quasars eventually quieted as their fuel supply dwindled. And now, 13 billion years later, those black holes sit quietly at the centers of large galaxies, including, possibly, galaxies not far from our own. The Milky Way's central black hole, Sagittarius A, may have gone through a quasi-star phase nearly 13 billion years ago. There is no observational evidence specifically linking Sagittarius A to the little red dot population. The Milky Way is too nearby for us to observe it, as it was at high redshift. But the physics that applies to the little red dots applies universally. If the quasi-star phase is how supermassive black holes grew in the early universe, then Sagittarius A, like every other supermassive black hole, likely passed through that phase. The black hole at the center of our own galaxy may have spent its first few million years hidden inside a dense hydrogen envelope, growing rapidly, glowing red, invisible in X-rays. A quasi-star in the early Milky Way. A direct ancestor of the 4 million solar mass object whose shadow was imaged by the Event Horizon Telescope in 2022. That is a remarkable lineage. And it suggests that the little red dots are not just distant, abstract objects. They are, in a deep physical sense, the origins of the structure we live within. Good night.